All right, let's jump right in. The paper is Being-H0.5, Scaling Human-Centric Robot Learning for Cross-Embodiment Generalization. This is the latest from the Being Beyond team.
And it is a massive paper. If you're working in robot learning, this is probably the one you need to be paying attention to right now.
Okay, here's the 1-minute summary for everyone. The core problem this paper tackles is what they call morphological heterogeneity.
Basically that every robot body is different.
Exactly, and that completely breaks the standard train once, run everywhere idea that we're so used to in, say, NLP. The solution they're proposing is a human-centric learning paradigm. They treat human hand motion as the universal mother tongue of physical interaction.
And to do that, they released UniHand 2.0, which is just the largest embodied pre-training data set to date. We're talking over 35,000 hours of data.
And the architecture behind it is a mixture of transformers design. It uses a mixture of flow framework to sort of decouple the shared motor skills from the robot-specific mechanics.
The results speak for themselves, really. State-of-the-art on LIBERO at 98.9%, RoboCasa at 53.9%. And they deployed it on 5 different real-world robots.
With a single model checkpoint. And the kicker, they actually showed zero-shot transfer to a robot on a task it had never been trained for.
It's a huge step. A really huge step toward a generalist robot brain.
All right, let's get into the weeds. This paper is really trying to solve what they call the Tower of Babel problem in robotics. For the ML engineers listening, why is this so much harder than what we see with LLMs?
It all comes down to the input and the output space.
Yeah.
With NLP, you have this kind of universal semantics.
Right.
If I train a model on English and French, there's a shared logic, a shared latent space, because concepts like apple or run map to the same fundamental ideas. But robotics just doesn't have that shared grounding.
Because the hardware is the ground truth.
Exactly. You take a Franca Emica Panda arm that has 7 degrees of freedom, very specific joint limits. Then you look at a Unitree G1 humanoid, a completely different kinematic chain.
And a P&D Adamu is different again.
So if you output a vector of motor commands that works for one, and you just feed it to another, you don't just get, bad syntax. You could literally break the robot.
A command like rotate joint 4 is meaningless if joint 4 doesn't exist, or it rotates on a totally different axis. So traditionally, we've just been stuck training individual models for individual robots.
That is the Tower of Babel. All these fragmented data silos. You can't just scrape the internet for robot data to train some foundation model because the data from a Boston Dynamics spot is just, mathematically incompatible with data from a robotic arm.
And this paper is arguing we've been looking at the whole problem the wrong way, that we shouldn't be trying to translate from robot to robot directly.
We need a lingua franca, a common language.
And their big bet is that the common language is us, human motion.
Yes. Think about the physics of a task. That's the constant. Gravity, friction, the way handle affords being grasped. Those things don't change. Doesn't matter if it's a human hand or a robot gripper doing the grasping.
So by training on human hand motion, they're trying to capture the intent. The what, not just the how.
The intent and the trajectory in a way that's agnostic to the specific hardware. The goal here is to learn the high-level plan from humans and then use a much more specialized layer to figure out the specific motor controls for whatever robot you're using.
And this lets them bootstrap skills for, say, low-resource robots.
Precisely. If you build a custom robot tomorrow, you don't have millions of training examples for it. But if your model has already learned how to pick up a cup from 16,000 hours of human video,
then you just need a little bit of data to fine-tune the kinematics for your new hardware.
Exactly.
Okay, let's talk about that data. You said 16,000 hours of human video. The whole data set is called UniHand 2.0.
It's a beast. 120 billion tokens, 400 million samples. It's something like 200 times larger than the data set for their last model, Being-H0.
So break down the composition for us. It's not just robot tele-up logs.
No, and that's the critical part. It's roughly 14,000 hours of robot manipulation data, sure, but then there's 5,000 hours of general visual language data, and that massive chunk, 16,000 hours of egocentric human video.
Egocentric meaning first-person view, FPV. Why is that view so much more valuable than, say, a static camera in the corner of a room?
It's all about solving the correspondence problem. When you're operating a robot or even just doing a task yourself, you're looking out from your own perspective.
You're focused on the hands.
Right. Egocentric video captures the optimal way to approach an object. It shows how a hand orients itself before making contact. It just captures the common sense of physics much more densely than a third-person view where your own body might be blocking the object.
And the paper says they didn't just scrape YouTube for this stuff. They built their own hardware rig, the Unicrafter.
Yeah, and this is a detail that's easy to gloss over, but for any data engineers listening, it's vital. The problem with web video, like from YouTube, is that it's just 2D pixels. You lose depth, you lose the camera extrinsics. You have no idea where the camera was in 3D space.
So the model might learn what a cup looks like, but it doesn't know how far away it is or how big it is in the real world.
Right. Unicrafter is this portable, low-cost rig, you can think of it like a wearable, that captures not just the video, but also depth information and precise 3D camera poses.
So it's feeding the model metric-aware data.
Exactly. The model isn't just watching a movie, it's understanding the 3D geometry of the scene it's in.
Which brings us to the architecture. How do you actually feed all this varied data into a single transformer? I mean, you have a human hand with 5 fingers and over 20 degrees of freedom, and then you have a simple robot gripper with just one, open and close. How does that even fit in the same tensor?
They use what they call a unified state action space. It's basically a clever masking strategy. So they map the global wrist pose, the 6-toe position and rotation of your wrist, to the robot's end effector.
Okay, so that aligns the reaching part of the motion.
That handles the arm. Then for the fingers, they have reserved slots in the action vector, one for the index finger, one for the thumb, and so on. If the robot is just a simple 2-finger gripper, all the slots for the other fingers are just zeroed out. They're masked.
So the model is always outputting this kind of super vector that could describe a complex hand, and the specific robot just listens to the channels that actually apply to its body.
Exactly right. It effectively tokenizes the embodiment. And this all feeds into their main backbone, which is a mixture of transformers, or MOT.
We're seeing mixture of experts, MOE, everywhere in LLMs now, like with Mistral and GPT-4. Is this the same idea?
It's a similar principle, but a different application. They split the architecture into 2 huge blocks. First is the understanding expert. This is basically a vision language action, a VLA component, that processes all the multimodal inputs, images, text instructions, everything.
So it does the high-level reasoning. I see a red block, the instruction says to pick it up.
That's its job. And the second block is the action expert. This is where the rubber meets the road. This part generates the actual motor trajectory. And inside the action expert is where they use this mixture of flow, or MOF.
Okay, this is the part I think we need to break down. Flow here means flow matching, right?
Yes, it's a generative modeling technique. Think of it as being in the same family as diffusion, but it's generally more efficient for things like continuous control policies. The real innovation, though, is the mixture part.
Right.
They realized that if you just train a single flow model on, say, a humanoid and a robot arm at the same time, you get catastrophic interference.
The gradients from one task fight the gradients from the other. Learning what works for the humanoid actually makes the arm perform worse.
Exactly. So MUF decouples the experts. They have foundation experts and specialized experts.
Okay, what does a foundation expert know?
The foundation expert learns the shared dynamics. It learns about smoothness. It learns that objects can't teleport. It learns the general physics of how trajectories should be generated. And this knowledge is shared across every single robot.
And the specialized expert.
The specialized expert is the router for a specific robot. It learns the particular joint delta distributions just for the Franca arm or just for the unitary humanoid.
So when the model runs, it's dynamically combining the general physics knowledge from the foundation expert with the specific hardware knowledge from the specialized expert.
It's a dynamic routing mechanism, and it prevents that forgetting problem. You can train on the humanoid without overriding the weights that control the arm, because those very specific weights live in a different expert, while the shared physics knowledge improves for everybody.
Okay, so that handles the training side. But deployment is where these kinds of generalist papers usually fall apart. The sim-to-real gap is notoriously difficult.
Oh, the reality gap. In sim, your sensors are perfect, your timing is perfect. In the real world, you've got sensor noise, latency, changing light conditions. The paper introduces 2 really clever infrastructure-level innovations to handle this.
Let's start with the first one, Manifold-Preserving Gating, or MPG.
This is essentially a built-in out-of-distribution detector. So when a robot is operating, sometimes the visual input gets ambiguous. Maybe a shadow falls on the object or there's motion blur.
And a standard model might just hallucinate a weird movement?
It might generate a jerky or erratic movement that's physically dangerous. MPG detects that the generated action is drifting away from the manifold, the space of safe, typical behaviors it learned during training.
And when it detects that, what happens?
The gate effectively forces the model to fall back on its robust priors. It biases the output towards safe, standard motion when it's unsure, instead of making a high-confidence mistake. It dampens the hallucinations.
And the second innovation is Universal Async Chunking, UAC. This sounds like it deals with the timing problem.
It does. Robots have different heartbeats. A really dexterous hand might need control signals at 50 hertz, maybe 100 hertz. A big industrial arm might only accept commands at 10 hertz.
And if your model takes, say, 50 milliseconds to run one inference pass, you can't control a 100 hertz robot in real time.
You're always going to be behind. So UAC decouples the inference loop from the control loop. The model predicts a whole chunk of future actions, say the next half second of movement, all at once. Then a separate asynchronous process just feeds those actions to the robot at whatever frequency its hardware demands.
So the brain thinks in chunks, but the body moves in a continuous stream.
That's a great way to put it. And lets them use the exact same model checkpoint on a fast robot and a slow robot with no retraining.
So let's talk results. We've got the data, the MOF architecture, the async infrastructure. Does it actually work?
The numbers are really strong. On LIBERO, which is a standard benchmark for long horizon tasks, they hit 98.9% success with their specialist model. But the really impressive number is the generalist model, the single model for multiple robots. It hit 97.6%.
That's a less than 2% drop for generalization. That alignment tax is usually way higher.
It's almost negligible. And on RoboCasa, which is a really complex kitchen simulation, they hit 53.9%. Now, that sounds low if you don't know the benchmark, but it is brutal.
And there's an interesting detail there, right?
Yes. Being-H0.5 actually beat methods like 3D-DP3.
Wait, 3D-DP3 uses point clouds, right? So it's getting explicit 3D data, and Being-H0.5 is just using, what was it?
Just 224 by 224 RGB video.
How does a model using 2D video beat a model using 3D point clouds on a 3D manipulation task?
Well, this is a huge debate in the field right now. The argument this paper makes is that the sheer scale of human pre-training, all 35,000 hours of it, gives the model such strong spatial priors that it can basically hallucinate the 3D structure accurately enough just from 2D images.
So it intuits the depth because it's seen so many hands interact with so many objects from that first-person view.
Experience beats raw measurement, at least at this scale.
But the most provocative claim, the one that really stands out, is the embodiment-level zero-shot transfer. This is the holy grail.
This is the magic moment in the paper. They took the PND Atom U robot, and they set up tasks that this specific robot had never been trained on. One was a flip and scan task for a package. Another involved opening specific drawers.
So to be crystal clear, the model had seen other robots, or humans, do this task, but never the Atom U.
Correct. The Atom U's specialized expert had 0 gradients for this specific task.
And what happened?
It worked. I mean, it wasn't perfect, but it showed task-consistent, multi-step execution. The robot understood it had to flip the box to find the barcode. It understood the semantics of the task from the understanding expert, and the foundation expert provided enough general motor control to drive this unfamiliar body through the right motions.
That is wild. It implies the model has a truly decoupled understanding of task versus body.
It suggests we're moving toward a place where the specific robot hardware is almost just an implementation detail. If you have a strong enough foundation expert, you can drive almost anything.
It's like the universal driver concept from computing. You install the driver and your OS can use the printer. It doesn't matter what brand it is.
That's a perfect analogy. Being-H0.5 is trying to be that universal driver, but for the physical world.
So to wrap up, the key takeaways here are really the massive scaling of human-centric data with UniHand 2.0 and this mixture of flow architecture that stops the different embodiments from interfering with each other.
Yeah, and if you're an ML engineer, I would highly recommend reading the ablation studies on the mixture of flow, seeing how they actually route the gradients between the foundation and specialized experts. It's just a masterclass in neural architecture design.
It really makes you wonder about the future of hardware, you know? If the software is becoming this adaptable, maybe we stop worrying so much about making precise, uniform hardware and just build whatever form factor is cheapest or best for the job.
Knowing the AI can adapt to it, maybe even zero shot, we might be witnessing the birth of a truly universal motor intelligence. It's not about programming the robot anymore. It's about teaching the model, and the robot just follows along.
Fascinating stuff. We will, of course, link the paper in the description for you to check out. Thanks for listening to this episode of AI Paper Podcasts.
We'll catch you in the next one.